All right, so hello everybody. Welcome back to our Center for AI Innovation training sessions dedicated to machine learning and applications of machine learning. Today, I'm very happy to introduce Priyam Mazumdar again. He's going to present a tutorial on how to get started using pre-existing models, in particular for places like Hugging Face. Priyam is very proficient with working with a variety of different machine learning models, and his tutorials are always very engaging and sort of hands-on. So I'm very happy that he agreed to present this tutorial today again. So Priyam, please take it from here.
Yeah, of course. So so I will be basically talking about this concept of pre-trained models, and the main reason for this is this paradigm really exists for just deep learning related problems, and you don't see it really in machine learning, and we'll kind of talk about why this is the case. Logistically, if you have any questions for anything, just stop me. It's easier if you just like talk out loud than put in the chat, because I might miss it in the chat. So yeah, just let me know. Right, so let's kind of talk about what this pre-trained model idea is, right? So intuitively, right, as we know, when you train these deep learning models, a deep learning model is really just nothing but a bag of parameters, right? You just have all these different parameters that express the different layers inside your deep learning model. And our goal is, through the training process, optimization, gradient descent, whatever you want to do, our goal is to find the best set of parameters that take the input and map it to the output with the lowest amount of error, right? Or the highest accuracy, or however we do it. So the thing is that when we do this mapping from, and in this case, we're going to be talking about images because I think it's the easiest to visualize over like NLP, but the ideas all stay the same, right? When you do this mapping from input to output, that learning or the knowledge, quote unquote knowledge that the model has is essentially expressed in those parameters. And now if we want to essentially take a model and then train it to another task or a similar task, then some of that quote unquote knowledge should transfer over, is the idea, right? So this is the whole purpose of pre-trained models, and they can come in kind of all sorts of types. So the example we'll be talking about mainly are models pre-trained on ImageNet, right? So I'm sure you've heard of ImageNet before, but just in case, essentially there's 1,000 different image classes, and our goal is, given an image, predict which one of those thousands it belongs to. Now, inside this ImageNet, some of the classes are dog, cat, wolf, things like that. There's other things like cars, buses, bridges. I mean, there's all sorts of stuff in there. And so if we want to train a model that just predicts dog versus cat, rather than all 1,000 of them, well, most of that, again, knowledge parameterized by all of those weights should transfer over pretty easily, right? There's no need to essentially train the entire model from scratch. We're basically going to start from a place where it works pretty well and just keep it going to optimize for what we specifically want. But we can also take a couple more steps further away from that, right? What if we wanted to predict some stuff that wasn't in that 1,000, right? In the 1,000 classes that ImageNet had? Well, this is also fine because a lot of the initial layers of a convolution neural network, right? And so there's some like light expectation here that you know what these terms mean, convolutions, like what layers are, some intro to PyTorch kind of stuff. But again, if you have any questions, stop me and I'll try to explain it as much as I can. Right, but essentially the initial layers in a lot of these deep learning models are really just doing basic feature extraction, right? So if in like, if you've ever taken like an image processing course, you've seen things like Sobel filters and all of that. And basically it's edge detection, searching for specific features, things like that. And then later, the later convolutional layers are doing more kind of image specific features is what we hope. So based on all of this, a lot of those initial layers, especially, right? All images have edges, all images have lines, all this sort of stuff. So we can definitely detect all of that and kind of learn the rest of it. So we're going to be doing it in a couple of different ways. We're going to essentially do a ResNet model, right? So ResNet 18 was pretty popular. We're just doing ResNet 18 to keep it pretty simple. And then we're going to be doing it from scratch, how PyTorch likes it. And then I want to go through the Hugging Face interface because it's just so much better in terms of stuff like this. They've done a really wonderful job of like documenting all these different models. So I'm just going to quickly, I didn't want to type out all the imports, but we'll kind of do the rest from scratch, and I'll explain line by line what I'm doing, right? So we have our standard set of imports here, right? So we're going to import Torch. we're going to import all our modules in Torch, the optimizer for PyTorch, our data set and data loader, so we can actually access these images. Different transforms, right? We have to make sure there's, what kind of transforms do we want to apply to an image, right? Our ResNet 18 and the ResNet 18 weights that go with them. Our image folder will allow us to kind of iterate through all the images we have, and that'll make sense in a bit. Transforms, right? These are all the transformations that I potentially want to apply. Summary is just a nice little way to see what the model looks like. If you're familiar with TensorFlow, TensorFlow will also kind of print out like each layer and the number of parameters and a bunch of information about your model. PyTorch doesn't really do that by default, so this will be our way to grab that. NumPy is, NumPy is like always. TQDM is just a progress bar kind of deal, and this is just a plot. Now for Hugging Face, we have a couple of different things, and this is probably the newer part for some of you, right? So Hugging Face's main API is called Transformers. That's the main package that they have. And then there's data sets. Then data sets is basically how we are going to access different things. But more important, we need to be able to load data set and load a metric. These all make sense as we get there. And then we are going to use these auto feature extractors, auto model for image classification, training arguments, and trainer, right? So again, this all makes sense very soon. So let's go ahead and take a look at our data set, right? So our data set is basically in this data folder. We have dogs v cats. There's a dogs folder, a cats folder, and then inside them, we have a bunch of images of dogs and cats. The caveat is that most of these images are not in the same shape, right? And so there's some issues. We need to make sure we homogenize everything before we actually pass it. So our path to data, right? It's going to be in the data dogs v cats folder, right? Dogs v cats, right? And so our data set, luckily PyTorch has a nice little function for us called image folder. And if we do our path to data in that, it should load. And then if we do for data in data set, if we print out the data and break it, we can see that our images are essentially returned as this is of image, and this is the pill image of that image, a tuple, and then the class, right? So 0 is a dog, I think, and a 1 is a cat is how it works out, or vice versa, whatever it was. So to be able to feed it into our, and for us to feed it into the ResNet 18, we want to make sure that everything is normalized nicely. So we're going to use the typical ImageNet normalizing kind of, mean and standard deviation, right? So if you haven't seen this before, basically, if you took all the images, so all images again have RGB, right? There's a red channel, green channel, blue channel. If you took the mean of all the pixels, then this is what you would get in the R channel, G channel, and the B channel. And then similarly, if you took the standard deviation for all of them. And we're going to use this to just quickly normalize our images. So we're going to have two different pipelines, right? Train, transform, right? And this is going to use the compose that we imported before from the transforms. And what do we want to compose? Well, we want to do a series of transformations. The first one will be to resize, right? We need to make sure all our images are in a shape of 224 by 224, and I need a second set of brackets around it, right? So we want to, because again, every image could be horizontal, vertical, some random shape. We need to make sure they're all the same. And then we're going to throw a random horizontal flip, right? This will help us curtail overfitting. So basically it'll just randomly flip the images horizontally, just so not all the images look the same, but we have plenty of images. So overfitting was never really a concern. We need to make sure our image is converted to a tensor, because without this, we can't really do anything with PyTorch. And once it's a tensor, we can then normalize it, right? We can actually normalize the images, and this will give us our training transformations. We also need our valid transformation, right? So validation, when we do validation, we don't really need to do any horizontal flipping. All we need to make sure is resize back to the same shape, convert to a tensor, and just renormalize it again. So this should work. Looks like there's an error. Positional argument tensor. Which one am I missing? Let me just double check here. Okay, good. I think I might have missed a parenthesis somewhere. There we go. Either way, that's the idea. And so now we have our training transforms and the valid transforms, right? So now we just need to go ahead and split our data set up. right? So if we do print, or we don't have to do a printer, we can do len data set. We can see we have 25,000 images. I want to do 90% for training, 10% for testing. So our train samples and test samples will be equal to, we can do the integer, it'll be two different integers. The first one will be 0.9, right, 90% times the length of that data set, right? And then the second one will be the length of the data set minus the same thing again, right? So that'll give me 90% and then the remaining 10%. So if you do train samples, right, we have 22,500 and then test samples will be the remaining 2,500. Now we can use the PyTorch random split to take a data set, split it up, train data set, val data set is equal to torch.utils.data, right? .random split is a function available in there. We want to split what? The data set, and the length is going to be, the first one will be the train, so train samples, and second will be test samples. Technically, you want to do a train test val, but that's okay. We're just kind of doing this for demo purposes, so it should be fine. And now length, and you spell that right, L-E-N-G-T-S, length, plural. There we go. Okay, good. And now we need to make sure that our data set, or we're actually applying these transforms to the data set. So if you do train data set, dot data set, so we want to grab the data set inside, you can see, and then we could do one more dot, or not that one, dot data set, and then dot transform, right? This is a none because there isn't anything in there right now. So we want our train data set to have the training transformations, and we want our test data set, test or val data set is what I called it. So we'll call it that, right? Val data set will have the val transforms, right? And this will make sure that as we grab each image from our data, we're passing each image through this kind of sequence of transformations that we are interested in. Good. So now we're going to go ahead and do the rest of it. So we're going to do three different versions, right? We're going to first randomly initialize the model. So we're going to create a model not pre-trained at all, and we're going to essentially train it from scratch and see what happens. So like always, I'm just going to kind of go through this, what do you call it? We're going to code up one of the training loops. And the reason I'm doing all this is so you can later see how nice the Hugging Face API is in terms of like batch testing a bunch of different models at once. So we want to train on CUDA. If torch.cuda.is available, it'll let us train on our GPU, else CPU, right? So because I have a GPU on this computer, right, we can train on CUDA. And technically, if you want to train on a specific GPU, right, I want to train on the first one, so CUDA 0. Right, so now what we want to do is we can define our model. So our model will be equal to, so again, you could technically code up your own ResNet if you want, but the whole purpose here is using models that already exist to solve some problem that you're interested in. In this case, it will be, solving this dogs versus cats problem. Now, let's take a quick look at this model. As you can see, right, we have all this stuff. There's all these convolutions, there's skip connections, there's all sorts of stuff in here, batch normalization, whatever you want. The thing we need to change is this at the end, right? So as you can see, the last linear layer, after it flattens the output of the final convolution, is going to take an input feature of 512, but like standard ResNet, it's going to output 1,000 features. We only need to output 2 features because we have dog and cat, right? So we need to take this out feature and update it to be 2 instead, or we can just replace this entire layer. Now, when we do this, right, we're essentially going to reinitialize this last layer only with random values. Now, that doesn't matter here because when we initialize this model, everything was random. But when we grab a pre-trained model, we often have to just fine tune this last layer essentially. So let's go ahead and do that. So if we do our model dot FC, right, because again, the last layer here was called FC, so fully connected. We can do model.fc, and it lets us know that this is the layer, right? This is the layer that we have initially. We don't want that. We're going to replace it with a standard linear model where in features will be, again, we don't want to change what's going into it, right? Because that will break it. We just want to make sure the out features is equal to 2 to make sure everything is the same. And I think by default is always true. So that's unnecessary, but there you go. So this will then go do that. And then if we take a look at our model again, we can see we now have in 512 and out 2. So we're good to go here. That gives us the model that we're wanting. You can do more changes, obviously, as if you want to really tune a model, but I have noticed the more complicated of a change you want to make, it's better just to start from the source code and then make the changes in there and load it in. But either way, that does this. And then we just need to make sure model is equal to model.to device, right? We're going to make sure it's sitting on our GPU for training. So there's going to be some training inputs we want, right? Training inputs, right? So we need the typical things, right? How many epochs do you want to train? I'm not going to train too much just so we can get an idea. Optimizer, so optim dot atom, we can do like the weight regularized atom for optimizer. And what do we want to optimize? We want to optimize the parameters model dot parameters, right? These are the things we want to actually optimize. And then we have a loss function, right? What do we want to do? Well, this is a what do you call it? This is a classification problem. So we can use either cross entropy loss or binary cross entropy, kind of works out the same. So cross entropy loss is what we will use here. Okay. And then the last thing is the batch size, right? So how many samples or how many images do we want to pass in every iteration? We can do 128 in this case, right? So that should be sufficient. Yeah, good. So now we want to go ahead and build the data loaders, right? Build data loaders, right? So what does this mean? So if we again iterate for, actually I never showed that, so this is a good chance to show it. For let's go here, data in trained data set. If we print out the data, and then break it just so you can see again. Last time it was like an image. This time we have a tensor, right? And this tensor will have it's a tuple with the first thing being a tensor and the second one telling me it's a image of 0, right? Which I think was a dog again. So if we grab the first thing 0, right, the first index dot shape, we can see an image has RGB channel and it's been reshaped to 224, just like we wanted. Well, we don't want just one image with 224. We want 128 of them at a time. So we need to build the data loader to do that, right? So our train loader will be equal to data loader. It'll take in the data set for the train data set with a batch size equals batch size, right? That's what I want. We definitely want to shuffle, right? We want to make sure there's an equal cats and dogs representation in every batch of 128. And we can set the num workers to 4 for now, right? So some more effort is putting into it. And then val loader, right? Same thing, val loader is data loader. This will be the val data set. Again, batch size equals batch size. In validation, it doesn't matter if we shuffle or not, so we can just turn that off. And the num workers equals 4 again, right? So there, that gives us everything we need. Now we need to write a actual training script and log how training is going. I wonder if it's worth doing all the logging, but that's fine. We'll just do it. If we're doing it, we'll do it right. So we're going to create a function called train. Our training function needs to take the model. It needs a device, right? What device will the model sit on? What are the epochs? How many epochs do you want to train? Optimizer, right? What's the optimizer we want to use? What's the loss function we want to use? What's the batch size we want to use? The train loader, actually, I don't think the batch size is used once. So yeah, that's fine. We can use that. And then the val loader, right? So these are all the things that's going to go into it. Good. So what do we want to log in training, right? So this is a image classification problem. So most likely we want to log the first, what epoch are we at, right? So we'll do that. We want to log the training loss, right? So what is the, how is the model performing? the training accuracy, right? So accuracy, so loss will tell us the cross entropy, right? What is the difference in distribution essentially is what cross entropy is trying to calculate. Accuracy is just what percent of the images in this batch have I calculated correctly. Then validation loss, right, will be here. And then same thing, valid in quotes, validation right? So that'll give me my validation accuracy, and that should be everything I want to log. So we're going to do 4 epoch in range epochs, but it won't be range epochs. It'll be range from 1 to epochs plus 1, just so we're starting from epoch equals 1 rather than epoch equals 0. Right, and then we're going to print out starting, let's see, starting epoch, and then just which epoch are we at, right? So, and this is an F string, right? Just so we can keep track of where we are in the training. And then we need to instantiate a bunch of stuff. So for every iteration, training losses, training accuracies is equal to 2 empty lists that we want to populate. And then validation, losses, validation accuracy is also 2 empty lists, right? So we're going to populate this as we kind of iterate through our data. So first we're going to do training data, right? And then second, we're going to do validation data, right? We have to do both of them. Good. So training data. So we're going to do for image label, right? So for every image label in train loader. And so the only thing I'm going to add around the train loader is that TQDM that I briefly mentioned before. TQDM doesn't do anything. It just prints out a progress bar so we can see how long training is taking and stuff like that. So it's just it's more of a logistical thing than anything else. You don't have to have it. We want to make sure the image and the label are sitting in the device. So image.to device, label.to device, right? That'll give us everything we need there. Now, just like every training script, we want to zero out the gradient, optimizer.zero grad. So the optimizer gets a fresh start for every iteration. So we don't need to do any kind of gradient accumulation here. Now our model, right? Now we're going to pass our images through our model. So out will be equal to the model dot forward. And inside the forward, we're going to add in all our images, right? So there we go. Now we want to actually calculate the loss. So the loss is equal to that loss function that we imported in. And we want to calculate the loss between what? The output of the model and the labels, right? So what the ground truth and our prediction. Now we want to calculate the accuracy. So how the model returns data, just to give an idea, is basically if we have 4 samples, let's say, or 4 batch sizes, and we're doing binary predictions for both of them, it'll be like 0.6, 0.4, right? So that'll say, oh, we predict the first one is 60% and the second one is 40%. Or sorry, we predict for the first image, it's 60% likely to be a dog and 40% likely to be a cat. And this could be like 0.4, I mean, it doesn't really matter, right? So for every image, we're going to get a list of what's our probability of likelihood for this image to belong to the class. We will say that our prediction will be the index with the highest value. So in the first one, it'll predict it's 0 is the highest one. The second one's going to predict that 1 is the highest one. So we need to essentially just grab those. So we can easily do that as our prediction is equal to torch.argmax on the out. And the index, or not index, right, axis is equal to 1, right? So this will go through each row and figure out which of them is the highest one, and that'll give us our predictions. And our accuracy will obviously then be where the predictions equal label, right? So whenever our predictions are equal to the ground truth label, that means it's correct, and so those will come out as true. Everything else will be false. So if it's true, we can add up all the trues together, which is adding a bunch of ones together, and we want to divide it by the length of the prediction, right? So that'll give us our percent accuracy essentially. And then we want to do training accuracies. I spelled that wrong. let's do that. Training accuracies dot append accuracy. Right? That'll give us that. And now we want to do loss dot backward, right? So we can actually apply or calculate the backpropagation step. And then we do optimizer dot step. And that will go ahead and do what do you call it? That will actually apply the gradient to the model and update all the weights. One thing we forgot is we also need to log our training losses. So our training losses dot append, right? And it'll be our loss dot item. And dot item is basically loss is currently a tensor that has gradient attached to it. We just want the numerical value, so we're just going to grab the item from it rather than the gradient and everything else. So that is our very simple training loop. We're just going to copy this and paste it for the test for the validation loop. All that really changes is we have a val loader here. So we want to make sure iterating through that. We no longer have any of these gradient calculations happening because again, we don't want the validation data to affect our training or the actually update the weights in any way. We just want to pass it through, calculate the loss, calculate the accuracy, append all that. We don't need to do any of this then in terms of updating any of the weights. We want validation losses and the validation accuracies, right? And then the last thing, just to save on compute, we can do with torch dot no grad. So this will make sure that as we're passing through, we're not like computing any like gradient maps or anything, so we can ignore all that. And that should be it in terms of our validation loop as far as I can tell, right? We're pending this accuracy, loss dot item. Yeah, cool. So that's our very simple, training loop. Nothing really fancy happening here. Once we finish a single epoch, right, we then break out of the for loop and we have to do a couple of different things. We can do training loss mean, because again, remember, we basically now have a list of training losses and a list of validation losses and accuracies and everything. So we want to find the mean of each of those. So then we're going to training act mean, and that's going to be np.mean of the training losses, and it'll be np.mean of the training accuracy. Sure, I spelled something wrong there, but that's fine. I'll find it soon enough. Valid loss mean, right? Valid loss mean, and then valid act mean equal again np.mean, or this will be validation losses, and then np.mean validation accuracies. There we go. So just because I'm sure I spelled something wrong, I'm just going to copy these in just in case. Okay, I think that's good. Well, we'll find out soon enough if something broke. Now, all we need to do is go ahead and log everything. I'm just going to copy this in just for simplicity. I don't want to print out all these print statements, but this is just to keep track of how things are going. Okay, good. So all we've done is essentially once a single epoch is complete, we go ahead and append to our list. This is the epoch we were at. These were the training loss, training act, valid loss, and valid act that we calculated for everything. And then we're just going to print it out, right? And then we're going to return from this our log training, right? So basically the log here and the model itself. And so now we're going to look at the log and the model will be equal to train, right? And now we can go ahead and train our actual model. All the arguments in here were model is equal to the model, and model is the ResNet that we loaded in, again, up here with no weights, no pre-trained weights, just a simple ResNet. The device is equal to the device, right? So that'll be, CUDA or whatever. Epochs is equal to, we'll train for 5 epochs here. Optimizer is equal to the optimizer. The loss function is equal to loss function. What else was there? There's batch size equals batch size. Go away. And then our 2 loaders, right? Train loader equals train loader, and then val loader equals val loader. Let's see what breaks. I'm sure something might. Okay, what happened? Too many P's. Append. Too many P's. Training losses. All right. Training losses. So append. There we go. Now try. Oh, I did it twice. Okay. Training losses dot append again. Up here. Okay, there we go. Now it's training. Great. So again, this is kind of your basic training loop. Again, if you wanted to do a more complex training loop, right? So what we've done up till now isn't really anything fancy, right? We're using the default learning rate of 0.01. I believe that comes with the optimizer. So you'll notice we didn't even set a learning rate here. When you see Hugging Face later, they have a bunch of cool features for us to kind of do different learning rate fun things, right? You can, we'll get into that in a bit. I'm sure something was going to break here. Oh, okay, I see. Huh. Let me just quickly grab this. Yes. Okay. So the accuracy, I did also need start item because these have gradients attached to them. So we can do accuracy.item and then accuracy.item. Let's double check. It broke on, sorry, I'm debugging as we go. Yeah, it looks like it was on that one. So let's just let that happen again. Yeah, so this is essentially our simple training loop, and we're training again from scratch, right? And our goal of this is now to show that if we load in a pre-trained model, right, what are the benefits? So as this is training, let's kind of talk about some of these benefits of pre-trained models. Main benefit is when you're dealing with the small data problem. I'll just keep an eye on this as it goes, right? So when you're dealing with the small data problem, and what I mean by this is typically in most research settings, you don't have millions and millions of samples to train your model, right? So if you don't have this, what do you exactly do, right? When you don't have a ton of samples, you either risk overfitting your model, right? Because you don't entirely know, right, you don't entirely know whether or not, when you actually go to fit your model, it'll just memorize the data set because you just don't have enough. But you fall into this weird dilemma that you need a more complex model to actually be able to break down this relationship between the input and output. But at the same time, you can't really scale the model up to the size you need it because you don't have enough data for it. So, when you don't have a ton of data, that's a great time. Second, compute savings, right? If all of ResNet, I think, has like 11 million parameters or something like that, this ResNet 18 model, if we only train the last layer or the last couple layers, we significantly cut down on the amount of trainable parameters, and we're going to be taking a look at that too. And third, right, predefined architectures, right? So it's a really good practice to understand how these models are physically constructed, right? So when we ResNet 18, these are kind of simpler models that people have been using for a while, but especially some of the more state-of-the-art ones, like vision transformers and there's all these like cool like SIFT types of models that exist now for these like vision tasks. It's good to be able to understand how they're implemented, and it's actually great to be able to implement it yourself or go into the code and really understand, but that's not really always the case, right? So a lot of these more advanced models that we see are implemented by entire teams of software engineers and stuff. It's out of the scope for kind of our own personal research. So being able to go grab existing models, existing pre-trained models, and reapply them for some new use case is a powerful tool. So you can see now it's training, everything seems to be working now, right? So after 2 epochs, we're at 73% accuracy. While that's going, we're going to just do the exact same thing, but we're going to now, instead of using a fully randomized model, we're going to grab the pre-trained model. And then with this pre-trained model, we want to just retrain the entire thing. So we're going to grab pre-trained ImageNet weights, but we're going to still train the entire model from start to end, right? So this will be model is equal to ResNet 18. Right, let's get it going down a bit. It's fine, letting it going. Right, so we want to grab that same ResNet 18 model, but this time we actually have weights, right? We want weights equals ResNet 18 weights dot default. Right, so these are the weights offered by PyTorch without us having to do anything, right? So these are basically PyTorch weights that they have stored for us to use on this. The first time you run it, it'll like basically download the model. After that, I won't do anything. So you can see, right, after 4 epochs, we're at an 82% accuracy. I think after 5, we're close to like 85 or something like that. I can't remember. Again, just like before, we need our last layer of the ResNet to be nn.linear, right? And we want to make sure we map to 2. So their in features was 512, just like before, and out features will be 2. We want to make sure we're mapping to 2. And then we again want to make sure model equals model.to device, right? We want to make sure it's sitting on the GPU. So yeah, it looks like we're at an 88% accuracy after training 5 epochs from a model from scratch. And so that's good to go. Again, we want to reinstantiate the optimizer. So optimizer is equal to optim.atom w, and then params equals model.parameters. Right, so these are the, we want to do this again, and then we can just grab all this again from here and just paste it in because nothing else has really changed. Okay, good. So let's only train this for 2 epochs this time because we actually don't really need to do much more than that. So now we're going to let this train for 2 epochs. So again, just as a reminder, this is us loading in ImageNet pre-trained models, but when we turn the last layer, the mapping of our flattened convolution final layer out to into a linear layer, and then make sure it maps to 2 outputs rather than 1,000 by default. This final layer, when built like this, is again randomly initialized and has to be something that's learned, right? So basically what we're trying to learn now, or what's remaining to be learned, is the mapping from the convolutions to the output, right, or 2 outputs. But in this case, we don't really have that because we're now training the entire model. So even though we've randomly initialized the last layer, we're still training all those convolutions at the very beginning of the ResNet. So right, so we're still losing some, or not losing, we're still kind of putting in all that extra effort in terms of training the entire model. And that's what we're going to do next, right? So instead of training the entire model, what if we only train the last layer or the last couple layers essentially? And so you can see with just 2 epochs, we're at 96% validation accuracy, right? Which is even higher than here. So we probably could have gotten to that with this model on this data set. We probably had to train closer to 10 or 15 epochs to get to that point. And this is kind of easily showing you, right? You can use pre-trained models and kind of use them on a lot of different things. What's actually interesting is that when some architectures are more general for all different types of tasks. So like I previously talked about the transformer, well, they have transformers for NLP tasks, right? So that's where like the BERT model, all that chat GPT stuff we've seen so far, right? This is all based on this transformer architecture that exists, or GPT. And then there's all these cool vision transformer things. But architecturally, other than some slight differences, they're essentially the same model for the most part. So if this is the case, and they're all the same model anyway, they actually did some really cool at Berkeley, I think a year or two years ago, some PhD students where they grabbed pre-trained like NLP models and applied it to vision tasks to see how well that transfer performance went. Right, so you can do all sorts of like cool transfer learning things, and there's like an entire literature on that. So either way, we're going to again grab all of this again right here. So this time, what we're going to do is instead of training the entire model, we want to go ahead and train only the last layer. Only this layer will be trained, and everything else will be stagnated, right? We won't have to update any other parameters. So we're going to freeze them. So let's go ahead and do this real quick. So if we do the summary of our model, and we know the input side, and this summary features that torch summary thing that I talked about before. If we know the input size to the model is equal to, size is equal to, it was a 3 by 224 by 224. Input size, there we go. Right, so we can see these are the number of parameters, right, for every single convolution, all the batch norms, all the stuff, right? These are all the things. And we have about 11,177,538 trainable parameters, right? So if we try to train this model again, it's going to try to do gradient updates on all of this stuff. But we don't want to do all of this stuff. We just want to do gradient updates on this very last linear layer. Just so we'll essentially only have to train 1,024 or 26 parameters rather than 11 million of them, which obviously is a huge computational save, right? So we can try that. So what we need to do is turn off gradient updates on everything else. So if we do for name param, in model.named parameters, we can first print out the name, right? If we print out the name, let's do method. I forgot to add the case. There we go. Right. So these are all the layers that exist in this 18. And you can see the main things are we want to turn off gradients on all of this stuff because it's been loaded in from ImageNet, and we trust that ImageNet weights are good enough for us. And we just want to train these last two. So you can see the names in the last two only have FC in them. Nothing else has an FC in them. So we're just going to add a rule that basically does that. So if FC is not, right? So if it's not in the name, then we want to print out the name. And then you'll see that we have everything, everything except for the its FC is not in. What was it? Oh, sorry, it's not is, it's just not in. Whoops, there we go. There we go, right? So we have everything, but those FCs are dropped out because FC was in the name for those. And for these specifically, we're going to print let's just print the param for the first one. So you can see what parameters look like, right? Parameters are also composed of this tensor, right? These are all the parameters that define that first convolution. And you can see at the very end of all these parameters that define that convolution, we have a device where the model is essentially sitting, or the parameters for this model, and we have requires grad equals true. We want to make this requires grad to false, right? We just want to turn it off. So we're going to do what we want to do is param dot requires grad equals false. And that should work, and it should be in place, so it requires grad like that. Okay. And then again, if we print out the param and look at the bottom, now we can see requires grad has been turned off. So requires grad is false, and so we're good to go. That will essentially, for all those layers that aren't the fully connected, we'll turn them off. And now we can do the summary of that model. And then the input features is again equal to 3 by 224 by 224. Or input, not features, it was input size. Sorry, that's my bad. Size. Right, same model, nothing's changed. But now we have oh, something has gone wrong. Trainable parameters. In model.
I think it's I think it, like when you showed the param dot requires grad equals true, I think it said like that parameters dot requires grad equals true.
Oh, it still showed true?
Yeah.
Oh, because you're right. Because this needs to be like this. Because it's like a function. There you go. Sorry about that. Thanks for catching that. There we go. Right now we only have 1,000 trainable parameters, 11 million, total parameters, 11, just a little bit less, right? Non-trainable. Thanks for the catch. That's very helpful. It's always like something small that I'm missing. So, okay, great. So, great. So we've essentially turned them all off. Now we can basically reload our optimizer from before and train this exact same model. No problem. So we can comment that out. Everything else should be the same, I think. So, yeah, okay, good. So this will just go ahead and train, but that's essentially what happened, right? So we should expect similar performance, or maybe even a little bit better by just fine tuning this last layer. And that's basically what's happening. So now, while this is training, I'm going to talk a little bit about Hugging Face, right? So Hugging Face is basically, the way I see it, it's like basically a giant library of models and data sets, right? So lots of people publish their models here that they've trained. Lots of people publish kind of data sets that they think are cool. And they make it very easy to essentially just access these things. But the main things is they have this tab on the left side whenever you go into Hugging Face, and they have a bunch of stuff here. Mainly it's here. They have text models, vision models, audio models, multimodal models, reinforcement learning models, time series models, and graph models. I'll make this a little bit bigger, right? So these are kind of different classes of models, and all of these models are available through the Transformers API, right, that they offer, which is great. So that's all we need to be able to do. I've opened up the ResNet one here because that's the one we'll be working with. And there's a couple things that you need to know about your model before you can use it. Mainly, you need to go into the forward function and take a look. So the first thing we always show you is how you can configure your ResNet, right? You can either configure it with the default stuff, or maybe you want to change some things for your ResNet. So you can, update it as you please. You can define your ResNet model. But the important part is in the ResNet model, right? Like every PyTorch model, you have to define a forward function, right? This forward function expects something called pixel values, right? Right. So we need to make sure that whenever we pass data to this model, that it basically the data we're passing to it is done through this thing called pixel values. Then there's all sorts of other stuff in here. So there's ResNet for classification that you can directly use. There's all sorts of models. But the cool part is the way you use the models is essentially homogeneous. So you can just pop in one model, switch out with another one without much of an issue, right? So you can see there's a whole list of these are all like vision transformer based models. They have a bunch of cool they have this one down here called VITMA that I do a lot of research with, right? So this is a unsupervised vision transformer model. They have all sorts of stuff in here, and like they're always adding more stuff to it over time. So it's like a great place. So you can see that this ended up with 97%. Makes sense. There's less parameters. More emphasis was just put on those last couple parameters. So good. Let's go ahead and start the Hugging Face stuff now. Okay, it's not me. Okay, great. All right, benefits of the Hugging Face platform, access to, access to state-of-the-art models in all domains, easy to extract. Oh, right. So let me actually just show this. Where are we going? Right here, right. So a couple things, right. So you have access to all these state-of-the-art models and kind of all these different fields that you can do. What's even cooler is they have kind of easy access to things like distributed training. So I know we had a distributed training, deep learning seminar a few weeks ago. You can definitely do all that if you want and have the time to kind of build it, or you can use Hugging Face's Accelerate platform, right? Which will basically do multi-GPU training for you without too much of a hassle, right? And then you can do even more cool things like hyperparameter tuning and all of that. So lots of really cool things that you can do with Hugging Face. Essentially, they're trying to build like a platform for everyone to use for their deep learning applications. So we're going to load it in. So Hugging Face ResNet 18, right? So the Hugging Face ResNet 18 model is called, it's under Microsoft, but they are the publishers of that paper, I believe. ResNet 18. They also have all the other ones, right? ResNet like 50 and like, I don't know, they come in all sorts of sizes. So we're going to be using 18 just for simplicity. Now, the thing we need to give it is essentially the mapping between the ID and the label, right? So we're going to set here ID 2. We need to create something that converts the ID like 0, 1 to label cat dog or dog cat, however you want it. I'll set it to, I think 0 is actually cat. You have to check which one is which, but label to ID is equal, and then we're going to create a label to ID, which is the same thing, just the other way around, right? So basically it'll be like 0 will be our cat, and let's say 1 is our dog, right? And then the second one will be the exact same thing, but instead of that, it'll be cat to, I'm sure there's a smarter way to flip things in dictionaries, but too lazy, so we're going to do this way, 0 to 1, right? So we have our ID to label and then our label to ID, right? So how do we go between them? Not entirely sure why it needs both of them, but it always asks for them, so it is what it is. Now, they have these things called auto models, right? So auto models, so like we saw in this config for ResNet, right? You can directly define your model right here, right? ResNet for image classification. The reason I'm using the auto model, so that's this one, auto model for image classification. The reason I'm showing this is you can essentially just drop in whatever model you want here, and everything else should be about the same as far as I can tell. So from pre-trained, right? We want to do a pre-trained model. We want to use, this is our like access to what is the name of the model we want. Then we want to make sure it gets the rest of it. So its label to ID will be the label to ID that we made. And then its ID to label will be the ID to label that we made. And then we need to add in one more thing in here. Ignore mismatched sizes equals true, right? So it's going to first load and pre-train this one. And then once it gets the labels, it's going to say, this model is supposed to output 1,000 things. I only have 2 things in here, right? So it's going to throw an error. We don't want it to throw an error, right? This is intentional. So we're going to essentially, right, we're going to ignore that. I missed a, let's see, 1. Oh, these are supposed to be commas, not period. There we go. And it's going to throw you a little warning here, right? It's going to say, hey, look, this thing that was supposed to be 1,000, I only have 2 here, and this, right? So here it will say you should probably train this model on some downstream tasks, actually be able to use it for prediction, which is great because that's exactly what we're going to do. This is also the place where we can do this, right? So we can essentially go ahead and take this model and then essentially turn off the gradient if we want to. So yeah, let's just go ahead and do that just to make training simpler, right? So this is exactly the same as before, right? We're just turning the gradients off, essentially. Well, it's okay. Let's not do it for now. Let's train the whole model and see what happens. So either way, let that be. Now we need to actually load the data sets, right? So in PyTorch, right, we use the image folder, right? Just as a recap, right? We use this image folder, and what image folder does is I have a bunch of dog images in the first folder or cat images in the first folder and a bunch of dog images in the second folder. So it basically says, okay, these set of images belong to this first class, these set of images belong to the second class. It's an easy way to load images for kind of a classification task. We will not be able to directly use that, but Hugging Face has their own image folder that you can use. So we're going to do dataset is equal to load dataset. We're going to use our image folder class, right? So we're going to do an image folder. And then if we want to use that, we need to give it a path, right? So this will be the path to data. I'm not entirely sure if you can directly use the PyTorch stuff with Hugging Face, because I'm sure they do some optimization internally for making like data loaders that are prepped immediately for like distributed training and all of that. So that's why we will just use what they have for now. And it works perfectly fine. So, and then what's the metric we want to keep track of? Well, you can do like F1 or, all these other different metrics that you can think of. You can even write custom metrics, but in classification tasks, generally all we care about that's not true, but for classification tasks, we initially just care about the accuracy, right? Obviously there's more than just accuracy, but we're going to be doing that. This is probably going to throw a warning, I believe. So this line of code takes a little bit of time to run. Essentially what it's doing is iterating through all of the data right now and creating a dictionary for us to access. So it's not actually loading the data itself. Otherwise, I would use up all of your RAM on your computer, but it is keeping track of the path to each of those data sets. So it's just doing that iteration process. That's fine. We can actually visualize this, right? So we can do the, let's say we want to visualize like the 2000th image, whatever it may be. We can do single sample. So that data set's going to return a dictionary. We want to look inside train because all we have right now is training data set. We're going to split it into train and validation in a bit, right? So we'll look at the 2000th image, and we want to grab the index, right? the correct index on that train. Now we want to do print. Well, I guess we'll be able to see if it's cat or dog, so we don't have to really print it out. Let's just single. Oh, there we go. Yeah, just do all that fun stuff. Yeah, it's basically just prepping the data set in the way it needs it specifically to train, which is fine, right? So it'll kind of do what it wants, right? But there is a little warning thrown here. Apparently this metrics equals load metric accuracy isn't the right way to do it anymore. You want to use evaluate.load. I just found that out about an hour ago when I was doing it, because this is how I always do it. But that's fine. If you have to use a different version, then you'll know based on your Hugging Face version what you need to do. Good. So single sample, and what we want to print out is the image, right? So it looks like clearly a cat image, right? So this is a cat, right? We can look at another one, right? 1,000, another cat. I think if we cross the halfway point, then like 20,000, whatever, maybe. Right now we're at a dog. Right, so here we go, right? Cats and dogs images, nothing too fancy. If we look at the data set itself, because I haven't shown that yet, data set, right? Our data set is essentially this data set dictionary that just has train inside it currently. And each of these return an image and a label. And here's the number of features. Well, we obviously don't want it to just all be trained. We want a training data set and a validation data set. So we can quickly do that. We can do split data set is equal to data set train, right? And they have a train, you can directly use the train test split attribute available in this. So you can do train test split. And how do we want to split? We can do test size equals 0.1, just like before. Shuffle equals true, and we can just set a seed for reproducibility. Now, if we look at our split data set, right? Now we have a training data set and a testing data set, right? Just like before. And now we can split it up. So we have trained data set, and then val data set is equal to the split data set. The first one is train, and the second one is the val data set, right? And this one is test, right? So that gives us our two different data sets that we want, right? So again, our train data set here. Which one did I do? Integer must be a, what did I miss? Let me just copy this in, make sure I didn't miss something. Okay. Not sure what I missed. I missed something, but oh well. Either way, yeah, I'm sure I just missed something small. Right. Either way. All right, good. So we have our, right, this is our trained data set, 22,500 images. Now, the thing is that, like we have two different problems here, right? So our data set is currently in a dictionary format, right? And we also need to be able to put the data together into a tensor form, right? So essentially, we need to essentially go from dictionary to tensors that PyTorch wants. There are some, I think they actually would do this for you automatically if you don't do much, but it is good to know how to customize your things. So first thing is that we want to actually transform our data set, right? So we made these transformations at the very beginning, this train transform and val transform. Well, we still want to make sure we're using these, right? Because we definitely want to have it resized to 224. Like at the bare minimum, we need to resize it because we can't do anything without that. It'll throw shape errors all over the place. So if that's the case, right, we need to make two different functions. We're going to create a function called def train transform, right? And this will be our train transformation, or actually def train transformation. We're going to pass in some kind of data dictionary to this train transformation. And what we're going to do is for every sample in data dict, which again is just a bunch of dictionary items, we want to create a new thing called pixel values, right? And we're using pixel values because we saw previously that ResNet's forward expects it to be called pixel values. And this will essentially be that train transform, train transforms image. The train transforms that thing from before where we resize and do everything for image in data dict image, right? So we're essentially creating a new thing in our data set called pixel values that's going to take in all the images and then just go ahead and transform them, right? And then we want to return data dict. Similarly, we want to do the exact same thing for our validation transformations, right? So this will be our val transformations, right? And then all that changes is we do a validation transforms, right? So this one basically skipped the horizontal transformation essentially. Now we just need to make sure we set these. So we're going to do our train data set dot set transform, right? Dot set transform, and we're going to set it to this one, right? So this is the transformation that we want. So every time it grabs a sample or however many samples, it'll pass them all through our transformations and set it to pixel values that we needed as before. And we need to do this for both of them, train transforms and val transforms. So val transformation, and this should be val transformation. Yeah, that's good. Val transformation, and this should be the val data set. Right, so there we go. That will go ahead and do it. And these aren't errors. These are basically just saying that, that's how it's storing in cache, like our dictionaries to all the different data sets. But this goes ahead and creates our data sets, right? With all the respective transformations and everything that you can think of. If we look at our trained data set, I believe, right? So everything else will stay the same. Nothing really fancy is happening here. Now is the part where we actually define the trainer, right? So there's 3 more things we need to do. We need to define the arguments of the trainer. We need to then, and then do metrics and a couple other things. So 3 more steps. So first, arguments, right? What are the trainer arguments that we want to do? So we have training arguments, right? And what are the things we want to do? Well, the first one is the name. Actually, there's quite a few things in here, so it's probably easier if I just copy it and I'll explain them all. So these are all the things we want for training. So first, this is again the name of the model we're training. And this is what it's going to use in the logging and stuff of how it's training. This is the name it's going to use to save it under. Remove unused column is false, because even though we're not using something, we don't want it to just drop it because we might need it later on. And it's just good to have everything in one place rather than having to reload it or re-access it again. We want it to evaluate and save after every epoch. We set the learning rate to a, 5e to the -4. But we get to some more stuff later, so we'll get to that. We then want to train 128, a batch size of 128. But what's cool is if your images are large or if your GPUs don't have the capacity, you can actually directly set things like gradient accumulation steps where essentially it'll split it and then just kind of pass multiple batches, smaller batches or sub batches essentially to your GPU, and then aggregate the gradient after the fact and then do the back propagation. So again, this would be quite a few lines of code that if you wanted to build your training script from scratch. We have the number of epochs, right? How many epochs do we want to train? In the case, we'll just do 3. Warm-up ratio, essentially, there's a bunch of like cool stuff that you can do with learning rates. So typically the ones you see is you can either have a constant learning rate, which isn't very smart. You can have a slowly decreasing learning rate. So as it trains, the steps it takes are smaller. Warm-up ratio basically starts the learning rate at a low value and then slowly increases it, and then it basically does other stuff afterwards. So it kind of gives and there's all these there's a bunch of literature on like annealing and different ways you can mess with the learning rate to get cool results or better results. Log every 10 steps essentially. At the end, right, if it trains for like 10 epochs and we see the 7th epoch was the best model, then go ahead and load that 7th epoch rather than the 10th one. And then metric, right, use accuracy as our best metric, right, whichever one has the highest accuracy. But if we want to use accuracy, we actually need to compute the accuracy, right? So let's go ahead and do that. So we're going to create 2 more functions. We're going to first create compute metrics, and inside we'll go evaluation, right? So what are the things we want to do? So essentially, this is going to be exactly the same as before, right? So we will essentially get a tensor, right, of predictions, and we need to predict for every row what was the argmax, right? What was our prediction for every row? So our predictions is going to be equal to np the argmax of our eval pred, right? So that's what came out of the model dot predictions, right? So we want the predictions from our evaluation, and then axis equals 1. This stuff, like why exactly it's formatted in this way, you kind of just figure this out by messing. If you train the model and then look at the output and then see, oh, okay, that's what it looks like, then you go back and add this stuff in. Or you can look at Hugging Face's documentation. They have a ton of stuff that explains exactly how the data is entered, right? The pixel values, how is exactly the data returned back out of the model. And then you can kind of piece all this together. And then we want to return what? We want to return the metrics, right? Dot compute. So what is the metric that we initially set? So we have accuracy, right? So our predictions is equal to predictions, right? Those are the things that we have. And our references is equal to eval pred dot label IDs, right? So the label IDs is our ground truth, and we're comparing it to the predictions, and we want to compute. If you give a list of metrics like accuracy, F1, whatever it may be, it'll do all of them. In our case, we just want to do accuracy. So there we go. The second thing is we need to make sure our data set, again, is in the format that Hugging Face or PyTorch is expecting it. So we need to create a function called collate. So this will make sense in just a second. So in a batch of samples called examples, right? Examples will basically be a dictionary, right? So we have a dictionary of all these different things, and we have already created something called pixel values. But each of these things in pixel values is a single image, not a batch of images. And we need to basically turn it into a batch of images. So we're going to do pixel values again, just to keep it the same. And it's going to be first, we're going to create a list, example, pixel values, because each image is going to have three things: a label, an image, and the pixel values version of it. And then for example, in examples, right? So we've created a list of all of the different pixel values of each image from every example in our batch of examples. And then we can do a simple torch.stack, right? Torch.stack will just take all of them and concatenate them on top of each other. And that is our basically batch of however many example images. Similarly, we have labels, which again will be that same torch.stack, but now instead of pixel values, we'll do example label. For example, in examples, right? So we're going to grab the labels from each one of them and concatenate them all together. And what we want to return is a dictionary of, again, pixel values, because that's what Hugging Face or what PyTorch expects and Hugging Face expects. And the pixel values dictionary will be the pixel values, and then labels in this labels is equal to labels. And this is spelled wrong. So there we go. And that does our collate function. There we go. So again, just as a quick recap, right? If we looked at our ResNet for image classification, you can see that the parameters at once are, the main things are pixel values and your labels, right? So you can calculate the loss and all that. And what does it return? It returns the loss, the logits, right? Which is our predictions essentially. But you can see the prediction shape is batch size. So if we had 128 images, it would have a 128 rows and config.none So in this case, we only have two outputs. So you'd end up with 128 rows by two columns, right? Cat or dog. So that's why we had to do this here, right? The np.argmax to make sure it's all kind of, kosher. So that does that. Good. So now we just have to make sure we can actually train it. So we can create a trainer class. And so this is our trainer. So remember, the first thing we did was training arguments. Now this is the trainer itself. What do we want to train? We want to train the model, right? We want to train it with the arguments specified before. What do we want to train it on? We have a train data set, which is equal to that train data set. We have an evaluation data set, which is equal to val data set, as we called it before. Scroll down. And then we want to compute the metrics. So compute metrics equals that compute metrics function that we wrote. And then we have the collator, right? So data collator equals that collate function that we wrote. Yeah. And so there's our trainer. Something has gone just a comma. There we go. We quickly take a look at our trainer. Right. So it's created this trainer class in transformers. And then all that's left is this, right? We can do trainer.train. And now it will hopefully start training unless I completely mess something up. Let's see. So labels equals torch.stack, example label, expected answer element 0. I might have just missed something small. So let's see. Let me copy it from what I have first, just to double check. Let's copy that in. Let's see. Okay, there we go. Start training. All right, so all of this sounds super fancy, but if we just change this ResNet 18 model to ResNet 50 or to Vision Transformer, they've done really well in keeping things very homogeneous, right? And I think that's a real power of like using this package. So let's just pick one that I work on all the time, right? So a typical one is, I don't know, let's just look at the Vision Transformer, why not? If we look at the Vision Transformer, right? Here's the model. There's a bunch of stuff that obviously goes into it. But if you look at the forward function, if we can find it, it's in here somewhere, we can search for it. Forward, here we go, right? So forward takes the exact same pixel values as before. So you could essentially just drop in the vision transformer inside there. I do that now, but that'll definitely run out of memory. That's a relatively big model. So yeah, you can see here it's training. Other benefits of this, again, in these training arguments, you can wrap this in the PyTorch, or not PyTorch, the Hugging Face Accelerate, and that will essentially then do multi-GPU training without much of a hassle. So yeah, so there it is nice to kind of have a platform that supports it, but again, by using a Hugging Face platform, you're also a little bit restricted in the amount of customization that you can do as well, right? So you're depending on their developers essentially rather than your own work. But you know, I use this stuff for my research all the time. It's worked out really well so far. So does anyone have any questions as this kind of wraps up training? Okay, yeah, so now it's doing a single set of validation. This is going to throw a couple of warnings. That's just how it is. Let me check that in the more chat just in case. Okay, good. There wasn't too many questions here. Shut here. Yeah, so the notebook I will put in the my Git repository. Something broke. Of course, something broke. Why wouldn't it? Metrics is not defined. I might have spelled something wrong. Was it this one? Where'd it go? Where is my metrics? Where are you? Because I did metric, not metrics. It's always something, right? Let's update that. And well, I'll just run all of them to be on the safe side. So let's do this one, that's fine. This is training samples. And I'll just let that train, that's fine. More important, this is kind of what the output will look like in the end, right? So as it trains, right, we're going to get kind of, this is a loss and accuracy. Now there is a little bit of a penalty you pay here as well. You can see the time per epoch has definitely gone up, probably a little bit, maybe like 20, 30%. But that's most likely because it's doing a ton of like logging and all of that in the back end. And so when you train something like this, it'll create like this folder called Hugging Face. It's going to create all these different checkpoints, kind of log runs. If you enjoyed using things like TensorBoard and all of this pipes into TensorBoard really well. So you can basically point your log DIRs, if you ever use TensorBoard, towards the runs, and it should just work without too much of a hassle. But yeah, this is kind of our typical kind of pre-trained model pipeline that I do. So again, just as a recap of what we've talked about here, right? So the power of pre-trained models, again, is it lets you deal with the small data problem because you don't need as many samples to train a larger model. And you could kind of fine tune to very specific tasks that you want. And a good example of this is like last year, there was all these groups working on essentially like, I don't know, they're basically working on these like different chemical kind of problems. And obviously there was a very small understanding of these different chemicals. And so when doing fitting like these cool NLP types of models on them, they're basically looking at all these different things. They just didn't have enough samples to train like something like a transformer model from scratch. So they started with a pre-trained NLP model and fine-tuned from there and got like surprisingly good results from that. Right, so you save on the compute, right? So less expensive on the computer. You can, if you're working on HAL, you can request significantly less resources. If you're only training that last linear layer, you could probably get away with training on your laptop, to be completely honest, as long as the model's not too big. And again, you can work with predefined architectures that have been like fine-tuned and optimized by like entire teams of people that have been working on this stuff, which is a really powerful tool. Right, and so we talked about cats versus dogs, right? And we did 3 different examples. We did randomly initialized models, so training from scratch with their own training script, and you get like decent performance, about almost 90%.
accuracy. But then once you start using the pre-trained model or the frozen pre-trained model, you get significantly higher performance because it's using a lot of that knowledge knowledge in quotes again, that it learned from all of the, what do you call it, from ImageNet, because ImageNet has a huge diversity of images, right? There's all sorts of stuff, and it forces the model to discern between dogs and wolves, which a lot of people won't be able to do in some cases. So because of all of this, it kind of works out really well in this transfer learning approach. And like I talked about, there's a lot of really cool research now on these multimodal transfer learning attempts, right? So going from like NLP to like proteins or NLP to vision and all this kind of stuff. So, you know, it's definitely a growing field with, there's definitely more questions than answers right now with it. So after that, we talked a little bit about Hugging Face. If you stick to the auto model for image classification, you can use almost every model in their API, but some of them aren't implemented yet in this, so you might not be able to use all of them. But if you went in and started dropping in different models here and just retrain it, it's a good way for you to essentially see which model might work best for the specific problem that I'm trying. They also have auto model for segmentation and other image tasks, and I'm sure they have all sorts of them for like reinforcement learning, NLP, all the other tasks that they're curious about. Right, so we use this. We can essentially, it loads the data set as a dictionary. There's a little bit of upfront work that needs to be done to do this. So when you do it for the first time, it'll basically build this dictionary, then cache it. And if you run it again, it'll access that again. So it's not too bad after the first time, right? For each of them, we need to make sure we grab each image and then store it in pixel values. I think this step could probably not use pixel values, but I like to use the same thing everywhere just so it's easy, because later on we need to access this one more time again to essentially collate them. So this is the best way to add those transformations we want from before, and you can basically do any transformation you want that PyTorch enables, or like there's all these other packages called like augmentations and all of that for fancier vision related transformations that you're interested in. You have to set ahead of time what are all the training arguments you want. What are the metrics you want to essentially track? And then you need to actually take the data itself and convert it to a tensor that would then be passed into your model. Again, you can do it this way. There's also, I tried to use what Hugging Face offers. You can also write your own training script essentially and just use their models, right? And I'll kind of explain that in just a second. Right, so we have, again, we just can then instantiate our trainer with all the different things and then just go ahead and train it. And this is using Hugging Face's internal training platform. If you didn't want to do that, right, if you wanted to write the training script yourself like we did at the very beginning, that is also super possible. Let's just pull up where it goes back here somewhere. There we go, ResNet. There we go, right? So they actually give great examples for all of this kind of stuff. So if you look here, essentially all you need to do is instantiate your auto image processor and the ResNet model. And then in that for loop, you want to do the inputs as just basically pass your set of images into your image processor. This will then return as a dictionary, which then gets passed into your model. And then you can do anything you want with it afterwards, right? So you can train this model completely using your own script, which I think is one of the best parts of Hugging Face, because you can decide how you want to do it. If you want to depend on their training platform and quickly deploy a bunch of models, you can do that. If you want to just train a specific model, but with your own training loop and your customizations, you can do that. It's really just up to you how you want to do it. So yeah, that's all I have. Sorry for the couple of bugs we ran into, but they weren't too bad. Is there any questions, or does anyone have any questions about any of this? Okay, cool. Yeah. So again, like I said, the notebook will be available, and the recording, I'm sure, will be uploaded in the next couple of days or so, whenever the NCSA gets around to it. So cool. Yeah, that's all I have then. Yeah, I'll be here for like another 10 minutes or so if anyone else has questions. But wonder if Dr. Kindertenko is there right now.
Yeah, Prem, thank you very much for this tutorial. Yeah, there is quite a bit of materials here. So I already received several emails asking, outside of this event, several emails asking about where the recordings are. So I think I think others will have to watch the recordings very carefully.
That's okay. Yeah. Yeah, of course. And if anyone has any questions, like after the fact, I'm sure my email is somewhere, so you can just like find me online and then just send me an email. I'm happy to help out however.
Okay, yeah. Thank you very much. We appreciate your effort with this tutorial quite a bit. This is very informative and very useful. Okay, so I guess that concludes today's session. We can stay online for a little while in case somebody has a question, but otherwise we are done for today. So thank you.